welcome everyone to the class of reservoir simulation. In the previous lecture, we talked about the flow equations that are used in reservoir simulators. And today's topic is about the discretization. What is discretization and how it is used in reservoir simulation? These are our topics right now. Discretization, types of discretization, and what is special discretization. Well, let's first define what is discretization. Reservoir discretization means that the reservoir is described by a set of grid blocks, grid points whose properties, dimensions, boundaries, location in the reservoirs are well defined. So let me show you the picture what is the discretization. For example, we have a well like reservoir like this one. Now this reservoir is big. Let's say is 100 10 kilometers, 10 km. This is the length of this the reservoir. But for example, what is the pressure at this point? What is the pressure at this point? What is the pressure at this point? What is the pressure? How much oil we have? Uh, how much oil we have here? How much oil we have here? How much oil we have here? Or how much? It's a 10 kilometer. So by considering it a one body, one reservoir, it is very hard to detect the properties in all over the reservoir separately. So what we do in this case, uh, we same reservoir we have here, we have the same reservoir. What we do, we divide into the small parts. We make blocks like this one. So you can say we divide it into Lego blocks. So now, for example, you are dealing with the uh, flow rate. So each of this grid block, this one, has its own address in X and Y. For example, this is X2 Y1. For example, this one is X5 Y1. This is X5 Y2. This is X5 Y3. X5 Y4. X6 Y5. So now each of this grid block has address, and we can define pressure, flow rate, saturation, porosity, permeability for each grid block separately. Here it was 10 kilometer. We couldn't define the porosity separately for because porosity probably is not uniform. Saturation is not same in all the reservoir. Maybe upper part is gas, middle is oil, and lower is water. But in this case, how you can define when you have only one body? So what we do, we divide into the blocks and we call it a discretization. So the process of converting this big reservoir into the small pieces of blocks, we call it a discretization. Now in this discretization, yeah, so now in this discretization, it all the proper dimension, boundaries, location in the reservoirs are well defined in this case. And now what is this discretization? Like this is the physically we divide into the blocks. Now discretization process, we actually do two kinds of spatial discretization we call it, and time-based discretization. The spatial discretization is based on the distance. We will talk about it, and then time is based on the time steps. Now we have two kinds of discretization as we discussed here. We have spatial one discretization, and we have time discretization. Two discretization. We have to define the geometry of the reservoir, cell dimension, how big or small the cells are, and the compressibility. Here we based on time because, for example, you are producing a well, uh, you are producing this well. Okay, now pressure initially right now, here right now maybe it's 2000 psi, but after 2 years pressure becomes 1000 psi. So based on the time, actually the situation is changing. So we have to, based on the time, we have to change discretize it and check what is coming tomorrow, what is coming after. We have to predict future, and we have to look at the past also, do the history matching also. So time discretization is important. Special discretization means, for example, again you have the this situation of the well, and the saturation here or the saturation here, they are not same, they are different. Or saturation here or saturation here, maybe here may be oil, here may be water, this may be water, this may be oil, or above may be a gas. So saturation is also changing. So we have to divide this into the small grid blocks like this one. We divide into the grid blocks, and then we define the its properties separately. So we divide into like this one. We define them. And the same is then we have a big reservoir, and we convert into the small grid blocks. Now we have one-dimensional grid block, two-dimensional, and three-dimensional. Here you can see one dimension. The one dimension means whatever fluid we have, it is moving in a straight line ahead or behind. So here you can see either it is going in this direction or it is going in this direction. So we call it a one-dimension one. Then we have two dimensions one. Here in from here the fluid can flow in this direction or this direction or in this direction or in this direction. So it has two directions. Either it can go in x direction or it go in y direction. So it is two-dimensional grid block. In the reservoir, our real reservoirs are actually 3D, three dimensions. So it can go in this direction, in this direction, and in this direction. It has three directions. So this is the one-directional system grid, and we call it a blocks, grid systems. So this is the one-dimensional, this is the two-dimensional, and this is the three-dimensional grid blocks that we have here. Well, the whatever grid size we use, usually we use the rectangular kind of thing, like them, like this. We use the rectangular in form, and sometimes they are in size regular, sometimes they are not regular. It could depend on the saturation and properties and so on. And for the one dimensional, we define the grid block in only x direction. Nx, we define it using nx, uh, nx. Or if we have two dimensional one, as I showed you in the previous video, like previous slide, nx by ny. Or in the three dimension, we have x, y, and z in three dimensions. So here you can see we have only x direction. Here we have x and we have y. Here we have x, we have y, and we have z. X, y, z, three dimensions we have here in this case. Now each grid block has the address. For example, address in this one, address here is, we define it by ijk. So for example, the first one here is the 1, 1, 1. Or for example, this one is 1, 2. This one for example is 1, 3. This one for example is 1, 4. This one for example is 4, 1. This one for example, this is the address of it. So we can set up properties based on their addresses and then do our simulation job. 4, 3, 4, 4. So here this is the x in one direction because and this is in x direction, and this is in y direction, and this is in z direction. So for example, this one is 1, 1, 1. This one is 1, 1, 2, 2. This one is actually 3. This one is actually 1, 1, 2, and the third one, this one was 3, the last one. So that's how we define uh, the grid blocks and their addresses. Now another important parameter here is the transmissibility values, and we have to find the transmission block, how the values are transmitted from here to here, from this block to this block to this block to this block. I mean the fluid is flowing here in this direction, in this direction, or maybe fluid is flowing in this direction. So we have to define the porosity, permeability, and others based on using this transmissibility values and so on. This is the discretization. Here you can see now how we define this discretization in X block. Let's look at it. This is important slide. Yes. So when we have three different grid blocks, for example, here we have uh, this is the number one grid block, this is two, and this is three. We have three different grid blocks. How we put the address? Well, these grid blocks are represented by X and I. Here you can see the symbol X and they are represented by X and I, or you can say delta X and I. So when we move ahead, we call it the forward uh, block. This is, you can say, the forward block. And when we move backward, this one is called backward block. So what we do, originally we represent with xi. So the forward block is represented by xi plus 1. So xi plus 1, as you see here, or delta xi plus 1. And the boundaries are represented by I plus 1 by 2. 1 by 2. So these are the addresses. For example, now you have another, you put another block here for example. So this will be x I plus 2, I plus 2, or x minus 2, then 3, then 4, then 5, and so on. So this is x minus 1 over 2. This is the boundary we represent by x I plus 1 over 2, or I minus 1 in the backward one, or backward block, or reverse block we call it sometimes. So these are how we represent the uh, in the x direction, as the focus is on block of I. So we start from the block I, then we go for I plus 1, and backward I minus 1. That's how we show the discretization. As I say, we have three different dimensions. We have one dimension, we have two dimension x and y, and we have x, y, and z. Three dimension here. So in one dimension we have two neighboring blocks. I mean, fluid can flow from here to here, or here to here. But in the two dimension we have four blocks to look at. So means more equations. Four blocks here. Here we have four blocks. And in this one we have six blocks. In three dimension, the fluid is flowing in six neighboring blocks in x, y, and z planes. Now we talk about the time discretization, calculation of production data. For example, production rate today is, let's say, 1000 barrels per day. Maybe after 2 days the production may be 900 or maybe 1100. So with time, we always say reservoir is alive. So reservoir situation is always changing. So what we have to do, we have to do the changes based on the time also. We have to do the time discretization also, divide the production into the time steps, discrete time steps. So now in this one we do the discretization based on t, because t represents the time step